we're going to use. TiO2 has a long history applied for photocatalysis, and because it's high activity and chemically stability and the non-toxic and it's cheap. And but however, for TiO2, we want to apply to CO2 reduction. It's still not perfect match to our requirement. It's valence band and the conductive band. It's not perfect match, and the gap is too large. So that way, TiO2 in anatase is only responsible for UV light. That it's visible light. There's no absorption. That way, so modification is necessary. There's two usually most commonly favorable in literature is doping and the surface metal deposition. For doping, there is metal doping and non-metal doping. For metal doping, it can modify the CB, conductive band of TiO2. In that way, can generate the new energy level, and that we can modify the CB and then can make it the light absorptibility to more efficiency. And for doping, there's two kinds. For small radium atoms, it can like vanadium and iron, it can use the interstitial doping in the space of a different lattice. And for the large radium atom like niobium and for large radium, it can replace one of the titanium atom and then squeeze out it and replace it in the lattice. But however, for we have to mind here if a too high concentration of doping metal, it can destroy the crystal structure of TiO2. That way can introduce some unnecessary defect that actually is not good for photoreaction. And then we have to mind we have to introduce a reasonable energy level in that way to avoid the hydrogen production, which is a competitive reaction in our case. Take some example like vanadium iron. This doping amount is only 5 atom%, and for niobium, its atom radium. A radial atom is close to titanium. That way, it can doping amount can be up to 20%. Then for the non-metal doping, not like metal doping. Non-metal doping is modify the valence band of TiO2. One of the most popular element is using nitrogen. Because even compare with metal doping, even it's okay, it can achieve a really low amount of nitrogen, but still can get a really good result for modification. And then for the surface metal deposition, it means deposit different metal particles in surface of TiO2. In that way, can improving the efficiency of electron transfer and inhibited the recombination of photogenerated electron hole pairs. That way, can easy CO2 reduction process. It exists as co-catalysis. And there's already a lot of metal has been tested in the literature to see its efficiency in CO2 reduction. And copper, because it has ability to construct the copper-carbon bond and the copper-hydrogen bond, that way it means it has potential to produce more value-added product. That's why it's really popular in CO2 reduction. And from even not just from doping and the metal deposition, we also consider it from the morphology of TiO2 to improve the TiO2. It's CO2 absorption capacity of TiO2. And aerogel is an interesting material. It has high specific area and high porosity. In that way, it's ideal material to prepare catalysis. And in our group has a long history to synthesis and application of a different kind of aerogel. One of example is using niobium doped TiO2 aerogel. It can obtain really small particle size of TiO2, and it's getting higher specific area, and it's quite stable. And so my subject was developed based on our previous work, which is niobium doped TiO2. And here we're using the solar gel method to synthesize gel, and then using supercritical CO2 dry to obtain the aerogel. And the formula we're using follow the previous work. So the design at the beginning is synthesis niobium and nitrogen co-doped TiO2 alcohol gel, and then synthesis the reloaded copper as the co-catalysis, and then we evaluate their performance in CO2 and water to produce value-added product. Also from the niobium nitrogen co-doped TiO2, first of all, we synthesis the different kind of niobium doped TiO2 from 1% to 50%, and from here color looking it's after doping the gel color shows a little bit yellowish. It's because of niobium doping, and then after we calcined in the air, we obtained the TiO2 alcohol gel with niobium doped, pure niobium doped, and compared with the alcohol gel, is color getting more yellowish. This is but with the different niobium doping amount, the color changes less obviously. This is maybe because the small density of alcohol gel. And then we're using a gas doping protocol to obtain nitrogen doping, which is catalyzing our sample in ammonia, then achieve nitrogen doping. Then after the nitrogen doping, the catalyst will pretend to compare with pure niobium doped sample is showing a grayish color, gray yellowish color, and this may be due to the generation of TiS3. And then we catalyzed our catalysis. First of all, use XRD to see the crystal structure. No matter, and our calcination is 515 degree. So even without niobium doping and with niobium doping, it's all showing anatase phase. After we zoom in the 101 peak, we observed that there is a blue shift after niobium doping, and it's stopped at 10%, which suggests that the doping amount could be maximal and 10% in our case, and the doping here is stopped at 10%. So which also agree our previous study. The blue shift is because even though the niobium ion at radium is close to titanium, but still at least slightly large. So that's why when it's injected into TiO2 lattice, it's gonna when this doping amount increase is showing the XRD, they're gonna be moved to a small angle. And then we check the niobium nitrogen co-doped TiO2 alcohol gel, this crystal structure. And first of all, we show anatase phase and also an observed anatase blue shift as before. And but from no niobium doped sample, we observed the rutile. This is maybe due to ammonia reducing effect. That's why its phase transfer temperature is slightly lower. And then we're using the XPS to characterize the surface electrostructure. From survey, we observed the different species, titanium, oxygen, and niobium. For the titanium, we observed the TI is stable and is showing TI4. And for the oxygen, we observed that there's oxygen lattice and oxygen vaccine, these two species. And the oxygen lattice is generated because niobium doping when niobium into the could replace with titanium because there is have to be a electron balance. So to achieve this balance, have to generate a electron to generate oxygen vacuums. And then it's niobium shown in niobium 5 as what we expected. And then it's for niobium nitrogen co-doped TiO2 alcohol gel. It's for the survey, it's the same. And for titanium, there is it's showing me is TI4, but in ammonia treatment, they're showing a shift. So maybe due to electron transfer between nitrogen and the titanium. And then we also observed the oxygen lattice and oxygen vacuums because of niobium dope. And the niobium was same as before. And from nitrogen, spectral, we observed even though it's not very clear peak as before, but we can see there's a trend peak. A trend is not directly, it's not zero, but there's a trend. Can see the peak of nitrogen hydrogen peak and the titanium nitrogen peak. This is maybe because our nitrogen doping amount is too low, so that's why it's during the test we cannot get a really clear peak. But even though from this trend, we can see the two species was exist. And then we from SEM to see our morphology of our alcohol gel. Without any doping, TiO2 alcohol gel is showing small uniform particle. It's like 25 nanometer, but after niobium doping, the smaller decreased particle size. It decreased to 22 nanometer, and even kerosene in ammonium, it's the particle size is increased, but after niobium doping, it's then decreased particle size is remain at 22 nanometer, which is also agree with our previous that niobium dope can decrease TiO2's particle size. Thus, we can obtain a good specific area. So we use nitrogen sorption to see its SBT. TiO2 niobium we get is kerosene in air had a very good very good value, and then after kerosene in ammonium, it's also get even though it's slightly decreased, but still remain a good value. Now compared with our result and TiO2 pure alcohol gel and doped alcohol gel compared with commercial catalysis P25 and other literature reference value. If niobium doped and pure TiO2 alcohol gel, our value is still one of the best SBT in the compare with the reference. And then we use UVVs to calculate our light absorption ability. The black line is commercial catalyst P25, and then compare with P25 and the pure TiO2 catalysis after niobium dope, its light absorption ability is increased, and there is a redshift because niobium dope. And can see from light absorption ability, niobium dope is increase its light absorption ability. And then we use in the procedure to obtain the band gap of TiO2. But from band gap, we didn't see a clearly decrease after niobium dope. So we think, but from the spectrum, we can see its light absorption ability is improved, but from band gap, we didn't see a big difference. So maybe we're thinking like niobium dope is working on it generated different energy level, or working on the color center like that in that way to improve its light absorption, but not working on band gap directly. That's why we cannot see from band gap it didn't decrease too much. And then we using the same UVVs to calculate niobium nitrogen co-doped sample. From here, you can see compare with P25, and it's getting more light absorption, and then compare with niobium within the kerosene air, and niobium and the nitrogen co-doped sample is getting even higher light absorption. And but the same as before, when we obtained the band gap, it didn't decrease dramatically, it's slightly decreased. So maybe same as niobium dope, the nitrogen dope is not working on band gap directly, but it's working on more energy level between VB and the CB. That's why it's didn't show in the band gap decrease. So we summarize our niobium nitrogen co-doped TiO2. We using the solar gel method obtained and then use supercritical dry obtained the TiO2 alcohol gel and with niobium dope. That way we obtained really high SBT TiO2, and we using niobium dope, we getting higher because it's a decreased particle size, and there's the blue shift we observed from TiO2 L101 after niobium dope. And with niobium dope, it's improved light absorptibility, and niobium doping also introduced oxygen vacuums. And then with nitrogen doping, we're using gas doping to achieve nitrogen doping. Nitrogen doping also improved the light absorptibility, and from XPS, we observed nitrogen hydrogen bond and titanium nitrogen bond. So after then, we try to load our catalysis copper. Here as we present here, after we use niobium to modify the CB and the nitrogen to modify VB, we want to modify the surface by loading copper. And copper was added during the gel synthesis. We added in the titanium source, and after gel synthesis, we obtained the gel, already obtained copper, and then using alcohol gel to catalyze in different condition. So with copper loaded, already contained copper gel, it's showing a blue, it's showing a green color. This is due to copper 2. And then with kerosene in air, it's getting a greenish color. This is also maybe due to a copper, but compared with alcohol gel, it's showing a little bit yellow. This may be due to niobium doping. And then we're using same procedure for achieve nitrogen doping. It's showing a even darker color compare the sample in kerosene air. This is maybe due to ammonia treatment, or maybe due to there's a generation of oxygen defects on the surface. That's why it changed the color. And the same as before, we're using XRD to characterize crystal structure. It's also showing anatase space, so it's same as before. But here we are saying we didn't observe any copper oxide species peak. From here, we can just only suspect maybe because our copper loading amount is low, or because copper is uniformed in the surface. That's why it cannot be detected by XRD in this so far. We need more characterization technique to see what kind of a state of copper. And then we're using to see the niobium co-doped sample. There is also observed the anatase phase and the blue shift, and without niobium doping, also with observed the rutile phase because ammonia treatment. And also from here, didn't observe the copper oxide species peak. This also as before, even in ammonia treatment, we didn't observe the copper peak. And from XPS, we so from a survey can see from different species, and the titanium remain stable. And for the oxygen, we see oxygen lattice and the oxygen vacuums. And then compare with copper with TiO2, it's oxygen lattice with the radio of vacuums and lattice. With copper, with niobium doping content increase, its amount is increased, but and still higher than pure TiO2 sample. And so this is also maybe due to copper loading, the oxygen vacuums is increased. And then for the niobium, same as before, we observed the niobium 5 as what we expected. And for the copper, we observed that there's copper 1 and copper 2 species in our sample. And but then we compared the radio, this bigger area of copper 1 and copper 2 observed in niobium. Pure niobium dope sample, the copper 1 compared with copper 2, the radio didn't change. It didn't change too much as long as the niobium doping amount change. So this is maybe due to the kerosene in air. The copper is not affected by niobium doping. So far, we didn't know a reason. And then we see from you can see from niobium and nitrogen co-doped sample, other species remain same. And for oxygen, we observe the oxygen lattice and the oxygen vacuums, and compare with niobium content. And here you can see within the niobium, nitrogen co-doped and the loaded coupled sample has highest oxygen vacuums. And then we see it from copper to see niobium nitrogen to co-dope to see what kind of gonna affect the copper. And as what we just mentioned, if it's kerosene in air, the copper 1 they will compare with copper 2. It's not changed as long as with niobium doping amount increase, but in the niobium nitrogen co-dope sample, it's way different. With the niobium doping amount increase, its copper 1 is increased, and then the 10% is up to maximal. So that's maybe suggest in kerosene during the ammonia treatment, copper and the niobium doping, maybe there's electron transfer. That's why the copper 1 is getting higher with niobium doping increase. And then we're using SEM to characterize its morphology. From you can see even loaded with copper, with metal, and we also the kerosene in ammonium. But our catalyst is our TiO2 particle still remains smaller. It's a smaller particle size. The maximal is around 30 nanometers, still small particle size. And Then we using the EDX to characterize its content of niobium to compare with XPS content with niobium and copper. For EDX, niobium compared with titanium is close to our input value, is 10. And for copper, it's slightly lower than what we expecting. This is maybe due to our our loading amount of copper is quite low, is 5%. That's why it's maybe during the EDX, it's not gonna um, detect the very accurate. That's why it's quite, maybe it's because that our copper result is lower than our expecting. And from XPS, it calculates the surface content of different species. For niobium, it's it's much lower than our input value. And for copper and without niobium, the copper on the surface is lower, and with niobium, the copper on the surface is much higher. This is also suggests maybe in the niobium, after niobium doping, the copper maybe has the electron transfer between niobium and also because niobium maybe introduce some surface defect, and that's why it can introduce more copper into the surface. And then we're using the nitrogen sorption to see its SBT of our different sample. And we can see from here is as before with just pure niobium dope, we get the highest value of SBT value. And then after calcining ammonia, it's a slight decrease. And then TiO with niobium, pure niobium dope, and with loading copper, it's decreased, but it still remain a quite good value. And then with calcining ammonium, it's still decreased a little bit, not a little bit. It's still decreased, but it's remain a good value. But we have to mention our catalyst is also loaded with copper, with loaded metal, and calcining ammonium, and but we still get a really quite good value. Even compared with commercial catalysis, it's much higher. And then we use in TEM to see what kind of state of our copper is. From HADIF, we can see observe the TiO2 101 and test 101 101 lattice, and we also observe the copper 2 and the copper 1 oxided 101 lattice. There's more clear to see this. This is agree with XPS result. The copper was exist as copper 1 and copper 2, and then we from the also the TM figure, we can see our particle size really small and distributed uniform. It's a really small particle. It's smaller, around 2 or 3 nanometer, and it was uniform on the TiO2. So we also using the UVVs to characterize with after loaded couple the optical property. And compare with P25 and pure TiO2 after loading copper with niobium, it's also first of all there's a redshift because niobium doping, and then it's much higher compared with pure TiO2 and the pure TiO2 niobium dope. This because this is maybe due to copper oxide and the cuprous oxide, their band gap, they have a visible light absorption, and in this from 515 to 1020, there is belongs to copper 1 and copper 2 oxided species. That's why here is much higher compared with pure TiO2 sample. And then we follow our previous procedure to obtain the band gap, and but still we didn't get in a dramatic decrease of band gap. This is also maybe copper was working because niobium nitrogen doping we explained not working on band gap directly. It's more generating new energy level, and for copper it's more exist as co-catalysis is not working on band gap directly. That's why maybe that's why our band gap is not decreased dramatically. And then we see the copper and copper with niobium and with nitrogen both sample, and with nitrogen doping is even more increased of light absorption ability from here compared to say, and also after obtained band gap, we also didn't see a dramatic decrease of band gap. Is also still because maybe because they are not working on band gap directly. but we can see from a spectral, it's the light absorptibility is increased a lot. And then here we summarize our copper loaded sample. With we follow also solar gel method and using supercritical dry, we obtained with even loaded copper, we obtained a sample with high SBT. And with niobium dope, we're getting even higher because it decreased particle size. And there is a blue shift also observed in the test when the one peak. And with nitrogen doping, getting more copper 1 in nitrogen doped sample, and also improve the light absorptibility. And for copper, we observed our copper as exist and a small, like 2 nanometer particle size, and that's why we didn't see it from XRD pattern. And with copper loading, also improved the light absorption. And for copper, it was uniformed on the particle size kind. And from these figures, look like the back of the ladybug. It's small and uniformed. It's really good. And so now we have the evaluation of our performance of our catalysis, and the test bench was built from our lab. The reactor we're using was from a homemade reactor, and the water circulation gonna control the temperature, and from a data collector as with the temperature and the pressure we're gonna be processed during the reaction, and the catalyst, the product will be analyzed by HPLC. And from here, we have to care for our reaction system because CO2 in the water, the solubility in water is really, really low. That's why efficiency, if using the pure water reaction, the efficiency is quite low. That's why we're choosing the one is sodium carbonate system. Another way our solvent will contain sodium carbonate, and during the reaction gonna purge CO2, and then illumination, and then we analyzed our system. And to compare with this, we're using another called bubble CO2 system, same procedure as a sodium carbonate system, but we didn't edit it, but only with copper and CO2, bubble CO2. So for the CO2 sodium carbonate system and the room temperature, here we choosing. For our pure TiO2, here also was have same performance with P25. Our pure TiO2 is it's only anatase phase, and for P25 it's a mixed phase with anatase and the rutile phase. Even though our is only anatase phase, is already has same performance with P25. It's showing maybe it's because the higher SBT is working in here. And then we want to see maybe what kind of doping factor gonna affect our performance. So for the TiO2 doped with niobium and nitrogen, we're getting higher. We getting higher performance of methanol production, and then we want to see what kind of effect copper gonna do. And see with copper, if compare with doping, it's the copper co-catalysis getting higher. So we want to see maybe we combine with copper co-catalysis and also with doping, and we can get in what kind of effect. So with copper with niobium, it's already getting even higher. And then we see with copper and niobium, with copper with nitrogen purely, it's also getting a higher. So then we put all of these 3 elements together to see that we obtained one of our best, it's our best performance. And we compared our catalysis with niobium and nitrogen. After we find with higher copper 1 sample, it's getting higher methanol production. And we traced the methanol production with time, and we can see, and the first it's increased dramatically in the first hour, and then increased stable. So it's accumulation reaction. So from here, we can see our catalysis niobium nitrogen doping improved the methanol production, and our copper also significantly improved. And pure for TiO2, our SBT definitely helped for the reaction going. And so then we were thinking choosing our best catalysis for its recyclability. And the first two round is remain a good value, and then it's performance getting lower, we lose some activity. So it's still remain a good value, but it's, the activities so we're losing some. So we're thinking what what happened during the reaction. So the after reaction, the catalysis was analyzed. The used catalysis for the STM, it didn't change too much. It still remains small particle size, and it's still uniform. So the morphology is not the reason for losing activity. And then we see the for the XPS, for the electron structure of copper. You can see after the reaction, the copper 1 is all disappear, only copper 2 exists. So we think maybe this is the reason why we lose activity. The copper 1 is all transferred to copper 2, and then we lose some part of activity. And then we see the temperature effector for our base catalysis, and the low temperature for sodium carbonate with getting quite a low methanol production, and then after higher temperature to room temperature, and it's increased, and then we even higher, getting higher 45 degree, it's getting even better methanol production. We think in the sodium carbonate temperature is good for our reaction. So now here we were thinking our gel, the alcohol gel we were using, this formula is follow previous study. So it's obtained a really small particle, like 22 nanometer TiO2 after loading copper, it's 30 nanometer. So we want to change the morphology and to see if it's gonna affect our performance. And we change from the formula of synthesis gel, or one change the isopropanol with the solvent, and one change acid and water to get into to try to change the morphology of catalysis. So the first one is our used the one we were used, it will get 30 nanometer smaller particle. And the second one actually is because it's close to my formula, so that's why the morphology didn't change too much. It still remains 30 nanometer and the small particle is uniform. But the third one is way different than mine. It's on the same scale. It's really small particle. I even barely can measure the size. And from here we can see even on the same scale, it's like a net structure. So this one we were getting a high expectation to see if its performance. So and then we using SBT to run nitrogen sorption to see if it's SBT. So this one I already used, and after change the solvent, it's increased a little bit. But for the last one, we were getting high expectation. It's almost twice than mine SBT. So this one is also getting way different morphology, and it's getting really high SBT. So we were thinking maybe this one gonna get a good performance. Then we applied for sodium carbonate system. For this one, for the the first one is mine already used. Then the second one is change and solvent. Its basic morphology is close to mine, and but the performance also close to the one I obtained before. But the third one we were expecting a really good result, and the low temperature its performance was really good. Then after we increased the reaction temperature, it didn't change too much. Then we getting even higher temperature. It's also still didn't getting a good value. So we wonder what happened during the reaction. So. And after reaction, we the first time observed that after the reaction, there's a red dot deposited on the window. It's so we think maybe during the reaction, the structure of our catalysis changed. So the XRD was used to see what kind of crystal structure is changed. So before catalysis, before the reaction, the catalysis remain anatase phase, as what we expecting and what we were obtained before. And after reaction, we observed the cuprous oxide peak, 111 peak here. So cuprous oxide was observed. This is maybe why we saw the red dot on the window. And this is also maybe why we're losing activity, because it's not structure, it's not stable. Cuprous is it's away from TiO2, so it's getting away from TiO2. and it's not going to become co-catalysis, it's just separated. And then we choosing our best catalysis for compare with sodium carbonate to using bubble CO2 system. So the first one we're using is purge CO2 and purge CO2 in water within the room temperature. Here we get a really low, methanol production, and the room temperature. And we compare with our case way low than our sodium carbonate system. So we're thinking maybe it's because in the pure CO2 bubble system, with the temperature increase, its solubility in water is decreased. That's why we think maybe decrease the reaction temperature, solubility gonna be increased. So here we lower temperature to 50 degree. And as it didn't, and the methanol production was increased immediately. It was match our expectation, and then we were adding to maybe due to solubility, so we added the sodium hydroxide to then we can get more CO2 in the water. And we and even in the low temperature, we obtained a really good value of methanol production. And then we increased the temperature to 60 degrees to see what in the sodium hydroxide system is how it's gonna be performance for methanol production. And but in here we observed after reaction, our catalysis was completely dissolved. And this is actually a very typical pre-treatment for from TiO2 powder to make to produce TiO2 nanorod or nanotube. It's a pre-treatment to dissolve TiO2 in base. But usually this reaction needs to a reaction in high temperature and high pressure. But in my case, it's in the it's really low temperature compared to their reaction. It's almost 100 to 200 degree, but mine is 60 degree. It's already happened, and it's atmosphere pressure. There's no added pressure in here, but also dissolved. So it's also an interesting finding. It's like a special finding during this. So, but anyway, but the catalysis was dissolved, so this result is not reliable. So we added the new catalysis and react in room temperature to compare with sodium carbonate. And here we added the sodium hydroxide and the new catalysis and react with the room temperature. So after increased solubility in water, it's CO2, the methanol production is increased. So that's why maybe for CO2 reduction, the solubility in water is way different. So the system choosing is really important. And then compare our catalysis with our best catalysis with some result in the literature. And because it's a different catalysis, and they were using different system, and there's some they use pure water, sometimes they use organic solvent, so it's difficult to compare, but try to find some similar to compare. In per hourly, our work is already get good results so far, but this one is especially high because this one only react for 1 hour, and so we compared our first hour yield of methanol is also comparable. So that way, our catalysis actually achieved one of the best methanol production in the so far from literature report. And now we summarize our performance. With liquid solid system and the gas liquid solid system, which is a sodium carbonate and the CO2 bubble system, we obtained, we compare each other. We can see our co-doping and the loading is also both enhanced methanol production, and we also get one of the best catalysis. And then for the CO2 bubble system, the solubility is the key to improve its methanol production. And for our key finding is nitrogen nitrogen co-doping is a significantly improved methanol production because it's improved light absorption. And for couple loading also is significantly enhanced efficiency. This is due to the electron transfer efficiency. And couple 1 to couple 2 conversion may be caused to losing some activity. The increased SBT for that sample, we were getting high expectation, didn't leading a good result. This may be due to the structure is fragile and it needs to be stable. And also from even no matter from sodium carbonate or CO2 bubble system, the temperature play a significant role in the reaction. And then we conclusion my all work. From aerogel, we take advantage from aerogel. It's obtained high. We can obtain high SBT catalysis, and with niobium doping, we even getting higher SBT because it's decreased the particle size. And with niobium doping, also improve the light absorption, and niobium doping also improve the methanol production. And with nitrogen doping, we getting more couple one. And niobium doping also improve the light absorption, and niobium doping also improve the methanol production. And for the copper, our copper is exists and the 2 nanometer particle size smaller, uniformed on the TiO, distribute on TiO2, and the copper loading also improve the light absorption, and the copper also significantly improve the methanol production. And this part of work was for the conference was presented on ECS meeting on last year, May, as Aura. And this part work also just accepted by Journal of CO2 Utilization from yesterday. And then we did some doping, we did some perspective for our catalysis. For doping, I know so far we chose niobium doping because follow our previous work. So now we want to change other metal like vanadium, and some to see is there improvement effect for TiO2. And for nitrogen doping, we were choosing gas doping, but from XPS we didn't see really clear peak, but just a trend of there is a nitrogen doping result approved. So we want to try using plasma doping to achieve getting higher nitrogen doping amount. And also for our TiO2 morphology, so far we're using particle, and we want to try to change TiO2 to different morphology like nanorod, nanotube, and to see if it's gonna improve our catalysis. And also we need to find a way to stable our the new net structure, the one we were tried but didn't get a good result. That one, trying to find a way to stable the high SBT. And for loading copper, so far the copper loading with the doping amount we didn't change. It's just chosen from literature. And so now we want to change getting decrease or increase the doping amount to see its effect. And we also need to stable copper one. We can see from my result, copper one is really good, really benefit for the reaction going. So we need to find a way to stable copper one species. And we also, because it's no time to present on the slides, but we also tried the impregnation method for loading copper, but we didn't get good results so far. We need to improve this method and to bring more copper oxide to the surface. And for the test bench, and here is so far we just mix the catalysis and with the water. It's invaluable for CO2 solubility. So that way we want to deposit the copper, deposit the catalysis on the window directly, then purge the CO2 and the water gas, and to avoid the solubility problem. And we also want to try to use different solvent to improve the CO2 solubility, because CO2 in water is quite low. So we want to try to use in DMSO and DMF such thing to improve solubility, and in that way to see how it's gonna be improve our reaction. And thanks to all of your help, especially from Pierre, Julien, and Cedric, and for Simon for the XPS, from Frederic and Gabriel for the XRD and the XPS, and thanks for the Muhad for the UVVs, and thanks for question. And, thank you all.
Thank you for your talk. So it's dynamic, very dense. So a lot of results, many things. So now we will start the discussion. So I give the floor to Valérie Keller.
Yes, can you hear me well?
Yes.
It's
yes.
okay for you? Okay, so first of all, I would like to thank Christian, of course, for his invitation to take part on that PhD review, let's say. The topic is, of course, very interesting for me, both from the how to say, for the CO2 photo reduction aspects, but also for the use of doping, co-doping strategies, and also for copper deposition approaches. I mean that each of these concepts could have been enough for one PhD, and you try to work on the three concepts at the same time. So congratulations for the lot of experiments you... Can you hear me, no?
Yes, yes.
Okay. But it's okay for you because I think that I hear my echo. It's not so pleasant, but okay. Okay, let's continue on that way. Congratulations also for your oral presentation. As said Corinne, it was very dense. Perhaps you could have chosen to select only the most relevant results because you put a lot of results in your manuscript, and perhaps I was waiting from you that you could extract the most interesting results because the oral presentation was very dense. So a few words about your manuscript. It was really clearly written. It was easy to read it. As I mentioned in my report, in my opinion, the first chapter, the state of the art, was a little bit too long, 85 pages.
Yes.
On less than 200 pages is almost a half of the manuscript, but I think some points could have been shortened. But nevertheless, you add a lot of references coming from the literature, very interesting. But I think you could have avoided to speak about too much things like molecular photocatalysis or CO2 reduction, and you may have focused only on the topic of your PhD subject. But nevertheless, it was well written. Okay. So I have a lot of questions. Perhaps I will not have time to discuss about all these questions. So if I will be too long, perhaps Corinne will stop me. So I wanted to discuss about both approaches, the co-doping approach and the copper loading approach. Okay, so let's start with the first one. What was, I would say, your idea by adopting a co-doping strategy?
Sorry?
You carried out anionic doping, cationic doping. What was the idea of using a cationic and anionic doping, and at the end, a co-doping approach? Could you explain me why the co-doping approach?
Yeah. So there's at the beginning for design the catalysis, our original desire was to get in to decrease the band gap. Yeah. So from here we want to see maybe to modify valence band and the conductive band at the same time. It can be more efficiency to decrease the band gap. So from modify valence band VB and the CB at the same time. So we'll say maybe doping at the same time. One is choosing the metal doping and one choosing the non-metal doping. And in that way can decrease these two parts at the same time. And that way the band gap can decrease more efficiency. Okay. And then for the metal choosing, because it's choosing from for metal doping, the niobium we chose is from the previous study, already the previous work. And for nitrogen doping, it's because it's more I read some literature for nitrogen doping. It's more efficiency for TiO2 modification. That's why this two element was chosen.
You mentioned that actually, how to say, you could have two kinds of doping mechanism, either interstitial doping or substitutional doping. Okay.
Yes.
Do you have an idea of the maximum of dopant element that you could introduce, enter inside the lattice of titanium dioxide for niobium, but also for nitrogen?
So the question is,
What is the maximum concentration of the different dopants that you could introduce into the lattice of titanium dioxide?
Okay, so for niobium, because it's ionic radium, is close to titanium, and from literature, it can up to, there's some report they can to up to 20% compared with titanium. But in our case, from example, is also for the previous work, our maximal doping amount is 10% compared niobium.
Okay, but
yes.
What was your doping amount? What was your doping concentration? Because if I remember well, you did not try to make a quantification of this dopant amount.
You mean like quantify its exactly amount?
Yeah.
Yeah, I should do this. This is something I didn't do. I should using for niobium and even for copper. I should use ICP to identify their exactly amount. But so far I only get the amount from EDX and XPS. One is from bulk and one from from surface. These two to compare. But yes, I should do it from ICP to identify its exactly amount.
Because how are you sure that you have not reached the maximum? For,
so this is from here we identify that from XRD.
Yeah.
From XRD, yes. Here the red shift, the blue shift is up to maximal at 10%. So from this we just say, yeah, it's up to maximal at 10%.
You observed also that you probably increase the volume of your lattice by doping.
Yes.
In my report, I mentioned the fact that it could have been interesting to follow the evolution of the crystallite size after doping.
Yes.
Do you have an idea of it's easy to, okay.
So for after doping, it didn't change too much. It's slightly increased, but not can say it, but it basically remains the same from crystallite size.
Okay. Okay. And okay, how could you explain it?
You mean the crystallite size didn't change too much? Maybe still because no low doping amount in our case. It's 10%. It's not quite high, so it's from XD. It's measure from peak position. It didn't too obviously to calculate it from there.
Okay, I'm not sure, but perhaps Corinne knows it better than me. Okay. Let's move to the copper deposition.
Yes.
I was perhaps a little bit lost because initially, what did you expect actually? To deposit metal copper or copper oxide spaces?
So for copper, it's the one I showed in slides is I writing the distillation I using the in situ method. Copper was added during gel synthesis. So even the gel, they already contain copper, but so far the copper exists as copper 2. And then we calcined in air and ammonia differently. In that way, copper can be oxided to copper 1 and copper 2 oxided. So from gel, it's copper 2 sodium, but after calcination, it's become oxided.
Yeah. Okay, because that is what you observed. But initially, what was the goal for you? To add a copper oxide species or metallic copper? Because on your oral presentation on slide 8, if you can go back to slide 8, please. Here you mentioned the advantages of metal copper used as co-catalyst, and you were not discussing about the different influence or advantages of using copper oxide species. You know what I mean?
Yes, I know. So here I just choosing from they are using metal state of different metal.
Yeah.
The copper should be 0.
Yeah.
But in my case, I just using copper oxided.
Yeah.
So yes,
So
yeah. It's not a really good example to showing here.
Yeah.
I should use in the copper oxided because even using copper oxided in the literature, there are still a lot of example. They were using for copper 1 and copper 2 oxided for CO2 reduction, and it's also get good performance. And from this slide, I shouldn't using copper 0. It should be directly using copper 1 and copper 2.
So let's continue on that topic.
Yes.
Page 145 or 146 in your manuscript. So you had calculated a bond gap.
Yes.
And to what contribution corresponds this bond gap, really?
For the band gap, I think from our case, it didn't decrease a lot. So I think the band gap I will measure it still for anatase TiO2 mainly.
So you mean that it is something like an average of the bond gap of the different species that you have on your composite material or not? I'm not sure that you can calculate an average bond gap. Do you understand what I mean?
I mean, like in the band gap, there should be others. Not just the TiO2. Actually, from this sample, there should be another absorption.
Can you show again the slide on which you have given the different bond gaps? Yes, here.
Yes. So here maybe so this side, this mainly is because TiO2. Maybe here is also another one.
Yeah.
Yeah,
so
maybe because
I mean that the bond gap that you have calculated here is actually a mean value coming from different contributions, because looking at your absorption spectra, you can see that you have a lot of contributions, some of them overlapping.
Yes.
So it's perhaps dangerous to calculate the bond gap as you did it, because it gives you an average value.
Yes.
Coming from different contribution. You know what I mean?
Yeah, it's not easy to see which range is belong to TiO2, which range become of copper oxide. So it's just take one point. It's not it's risky to say it's belong to TiO2.
Because according to literature, you may have here different contributions. A contribution from copper oxide, copper 1, at close to 1.5 electron volts, another one due to copper oxide 2, close to 2.2 electron volts. And in my opinion, at the beginning, between 40 and 550 nanometers, you may have the fingerprint of the plasmon of metallic copper. What is your opinion?
Maybe from ammonia treatment, maybe there could be some copper zero generated. Yeah, but because from XPS, I should do the LMM. Should do that to see if there are copper zero. But I skipped the part. I just see from XPS from copper 2p directly. Just only check from copper 1 and copper 2. Didn't take care of if there is copper zero. Yes.
Because in this case, the different contributions of copper 0, copper 1, or copper 2 may not have the same influence on they have different functions in the photocatalytic reactions, acting as a semiconductor. In this case, you may have the formation of heterojunction between different semiconductors, between titanium dioxide, between copper 1 oxide and copper 2 oxide. You may also have the deposition of copper zero. That means that you can have a co-catalytic function that could have a plasmonic function. So you have a very complex system, and it's not easy to distinguish the different contributions. That means that perhaps it's a little bit dangerous just to say that this is due to copper oxide, this is due to, you know what I mean? You have to be sure of the different contributions of copper. But it's not easy. As I said, just the copper deposition of titanium dioxide could have been just the PhD topic without the doping or the co-doping approach. So it's not
a really complex system.
So each concept needs perhaps to go deeper, but here you wanted to mix all these different concepts. It's not easy. And just, I remember now, coming back to the co-doping chapter 2.
Yes.
Page 115 or slide 19, perhaps. Slide 19. So typically in this case, looking at the absorption spectra, you can see that there's an increase in visible light absorption. Yes. But the band gap doesn't change a lot. How could you explain it?
Yes. So you were also surprised that because it's the spectral change, but the band gap didn't decrease a lot. So trying to find some just explanation to see what happened. So we are thinking maybe niobium doping is modified the conductive band, but it didn't generate a new conductive band, but it just generated a new energy level. It's not enough to a new CB, but it's just a new energy level. And the same as for nitrogen. It's so that's why it's maybe because of that the also nitrogen doping amount is quite low. That's why it's not going to generate a new VB, but just a new energy level. That's why the band gap didn't show decrease directly, but from light absorption, the spectral it's showing the more light absorption.
So are you sure that perhaps you are not in presence of other species that could absorb in the beginning of the visible part of the light? I don't know. Are you sure that you did not made carbon doping, for example? Or that you have some carbon-based residues that could absorb in that window of the visible light? I'm not sure, yeah.
Yeah, maybe it's some it's for during the test. It's didn't do it perfectly. Yeah, maybe this could be the reason because of the
it's
test.
strange that you are not going to lower the bond gap, but you have a huge visible light absorption.
Yes.
Yeah, it's strange. Yes. Okay.
Yes, it's it's weird.
So going further. So in chapter 3, page 124, it was not clear for me, it was not easy for me to understand what was dealing with in situ copper deposition. What do you mean by in situ copper deposition, actually?
Yes, so here we name the in situ because it was to distinguish from the another method, impregnation.
Yeah.
Yes, so and here choosing in situ because its copper was added at the beginning of gel synthesis.
Okay. Yeah. Okay.
Yes, that's why it was a synthesis at the with TiO2 gel, and it was inside of a gel. It's at the in the in situ situation.
Yeah. Okay.
That's why it's choosing this name.
So to do this, you started from copper nitrate precursor, salt, yes?
Yes.
And I was wondering, what about the remaining nitrate?
So after it was gel synthesis, we have a procedure called solvent change to replace the remained acid, the water, and the kind of impurity inside. So we were. It's from theoretically it should be all replaced after the solvent exchange, but then if there is the still remain of a nitrogen species, and it should be show up from XPS. But from XPS, even after nitrogen doping, without nitrogen doping, the nitrogen is just no single, it's just noise. So after nitrogen doping, there's still a small trend, a small single we can see. So from here, I just can maybe because maybe our solvent exchange already replaced all the impurity from gel to make sure everything is clean.
Okay, page in chapter 3, page 135. Could you explain me again what you mentioned, what you explained from the evolution of surface copper 1, copper 2 ratio as a function of co-doping?
Yes, here.
Yeah, for me.
Yeah, so here from compare with just nitrogen doping.
Yeah.
1 minute. So just nitrogen doping, copper 1 compared copper 2, the ratio didn't change a lot. But after nitrogen doping during the ammonia treatment, with niobium doping amount increase, copper 1 is increased. So here I was suspected the could be the explanation is during ammonia treatment, the surface niobium is getting higher, and the surface the surface vacuums. Surface vacuums, the defeat is getting higher, and the defeat is gonna trap the copper, and introduce copper more to the surface, and in the ammonia treatment, the copper was easily to reduce to copper 1. In that way, can getting higher copper 1 concentration.
So these XPS measurements have been done using ex situ XPS. That means that your samples have been stored under air. And are you sure that the oxygen vacancies could not be filled when the samples are stored in air, actually?
Yeah, it's a problem for XC2
Yeah.
XPS. It's probably it's not accurate to say the oxygen vacancy was already there. It's not. Yeah, but the proof we can get from just to compare with the nitrogen doping and nitrogen niobium co-dope. This just we can just compare with each other. We cannot compare with the same sample in situ and the ex situ situation. But from here, we can just say in the ammonia treatment, we get more oxygen vacuums and compare with no calcium in air. So in that way, just say yeah, ammonia treatment getting more and niobium doping introduce more oxygen vacuums.
Yeah, but it depends on the, how to say, on the kinetics of oxygen filling under air. Because perhaps one sample, you have perhaps measured one sample 2 days after and the other one 3 weeks after. Do you know what I mean? Yes. Okay.
Yes, it's difficult to just from XC to XGS to explain.
Exactly.
Yes.
If yes, to come back to chapter 3, page 126. So you describe the XRD results, yes?
Yes.
After copper deposition or after doping, let's say. And you saw the same XRD pattern that without copper deposition and without doping.
Yes.
And you mentioned the fact that there is no evidence for copper because you may have very small copper oxide domains, okay?
Yes.
And you confirm the presence of these very small copper oxide domains by means of TEM.
Yes.
And looking from BET measurements, you also observe that you have a decrease in surface area after copper deposition, yes?
Yes. Yes.
So how it is possible that so small copper oxide domains, 1 or 2 nanometers, can block the mesoporosity of titanium dioxide?
Yes.
I was wondering. Yeah.
This is the after we loaded the copper, we know the SBT gonna decrease because it's metal, it's heavy. So after loading, its SBT gonna decrease, and try to find all the reason might cost for SBT decrease, and the one that's for because it's a mass, and the second one tried for find some reason from literature. This can say because a copper particle size cannot block the pole of TiO2. But from our result, the pole size, the average pole size is larger than 2 nanometer. But it's just average pole size. There are still some really smaller pole, smaller than 2 nanometer, and this could be blocked by the copper oxide, the particles. And that way could be one of the reason to decrease particle size, the decrease of SBT.
Why not? Yeah. Okay. Yeah. If we can move to the photocatalytic assessment,
yes.
chapter 4.
Yes.
I was not finding the emission spectra or the irradiance measurement of the lamp. Do you measure it?
Here the light we were using is 100 watt of xenon light, and we didn't actually at the beginning it's not a thoughtful. We didn't using a filter to cut UV, so we were using the full spectrum of our xenon light, and the power of our xenon light, we didn't measure the exact value, so we just know it's a 100 watt of xenon light.
But the 100 watt is not it gives no information about the irradiance. It is just the electric power. And do you have an idea of the irradiance? I don't know, some 100 or 20 milliwatt per square centimeter. Do you have an idea?
From the instruction from the supplier, from the Xenolite, its instruction, it should be around 20 centimeters watts per centimeter, and yeah, but
20 watts per
we didn't.
centimeter.
No. I forget the exact value, but I just only get the value from the instruction. We didn't measure exactly the true value.
This is very important because
Mm.
at the end of chapter 4, page 185,
Yes.
you are comparing different photocatalytic activity, yes?
Yes.
And I think you have also written, if I remember well, that your photocatalyst, some of them have higher activity than the one mentioned in literature. But it is dangerous because you cannot compare. You are not sure that you have the same experimental conditions and that you have the same photon flux than the one mentioned in literature.
Yes.
So to actually to compare different photocatalytic activities between different experimental conditions, you have to be sure that you have the same experimental condition, and you have to compare, I would say, the quantum efficiency, taking into account the photon flux, the number of photons that your
Yes.
lamp is emitting or that your material is absorbing.
Yes.
Otherwise, you are not allowed to compare photocatalytic performance between
Yes.
different materials. Do you know what I mean? Yes, okay.
Yeah, it's using different solar light and using different condition,
Yeah,
and it's difficult to compare. So so when we compare with methanol production, should be careful with
yeah.
what kind of condition they were using. So yeah, it's
Because your higher activity is perhaps the results of different irradiance of the lamp. Perhaps you have
yes.
10 times increased irradiance compared to
Mm,
what is given in literature. So you
yes.
have to be careful about that, okay?
Yes. Yes.
Yes, another point, it was interesting that you use two approaches for methanol formation, one using CO2, one using yes, gas phase CO2, bubbling in water, in the
Yes.
solution, and
Yes.
the other one using sodium carbonate.
Yes.
I'm not sure, but did you perform the blank tests? I mean, without feeding with any carbon-based compounds. Are you sure the carbon in the methanol compounds comes really from CO2 that you are feeding or from sodium carbonate?
Mm.
Did you perform the test without feeding with CO2 or without adding sodium carbonate to be sure
No.
that there is not another source of carbon?
Actually, no. It should be. It should be to make sure which carbon is getting reduced. But yeah, the reaction I was doing is didn't to distinguish which carbon is getting reduced from
Yeah,
sodium
yeah,
carbonate or CO2 bubbles. So
yeah.
it's also didn't solve.
Because at the beginning we didn't do it,
Mm.
and one day we did it, and we were very surprised that we could produce carbon-based compounds without the addition, without feeding with CO2. And yes, and actually just some carbon residues on the surface of your catalyst may be enough to produce methanol or other carbon-based compounds. So you have to check this blank
Yes.
experiment also.
Yes. Yes.
Okay. If I have time, perhaps for a last question, a very last question. Yes, page 171. You did some experiment at different temperature, and it's very interesting And what did you find actually that the results obtained at 60 degrees are so strange? What did you expect from this?
The experiment at the beginning we did at the 60 degree. We try to do different to see the temperature effect.
Yeah.
Here, and the beginning this was designed to do at the low temperature, room temperature, and the high temperature. So high temperature, which was 60 degree at the beginning. But from a test bench, you can see our lamp was closed and a black box. So when I up the higher temperature to 60 degree, the black box was closed. And during the reaction, because it's overheated, so the lamp was shut down directly. So
Yeah.
actually the result is not accurate. So this result have problem. Then we try to do the temperature effect. So we lower the temperature, higher temperature to 45 degree. Then this way the lamp was safety. It can work normally, and that way we can get in a temperature trend. And so now the high temperature lower to 45 degree.
Yeah. Okay.
Yes.
So just at the end, you mentioned a lot of prospects, I would say approaches. If you would have 1 or 2 years more, what would be your priority among all these prospects that you mentioned?
So if I have time, I will try to do the plasma doping first. For now, I saw nitrogen doping is really potential. It's really good potential to improve the performance. So, but my nitrogen amount is quite low. So I want to try another way for nitrogen doping. And for copper here, I want to load in some noble, so more expensive metal to see like platinum and gold to see it's compared with copper or not. And for the test bench, so here I really want to try to deposit copper, deposit catalyst in the window. In that way to can the intact with catalysis with our base of a reaction. It's maybe gonna be improved.
Okay, so thank you again. Congratulations. You did a lot of nice job, a lot of work, and good luck for the future. Thank you.
Thank you.
Thank you so much, Valérie. This long discussion, but very interesting. A lot of points to discuss. So now I give the floor to the second reviewer of work. Christophe, you heard me? Yes, the floor is yours.
Thank you, Mrs. President. And thank you also, Christian, for this invitation. It was a opportunity to visit Nice, so I'm really sorry not to be here. First, because to make a report, it's a lot of work, and I have just that, and I miss the lunch and the drink after. So, and also because I cannot share the moment with you. So sorry, but let's talk about this work. So.
Yes.
It's an important moment, the defense, after 3 or sometimes 4 years of work on of research work. So really important to make to think about everything made. So first I try to look at from quite far, and then we will go a little bit more in detail. So when I received your manuscript, the first thing was it was quite heavy, more than 200 pages, but hopefully it was really easy to read. It is well written, it's not the point, but it is really well structured. The structure is very clear and really easy to understand what everything you develop in your work. So what I quite agree with Valérie is that the state of the art is take an important place in your manuscript, but it's very complete, and I think maybe you can publish only for review on this work. So I think really interesting also. My opinion when I wrote this your thèse, that it is a lot of reference because the state I mentioned more than 400 reference, so you read a lot of scientific work to understand your subject, and it is also made with really good illustration and explanation. Only 4 chapters, but really clear, as I told you, one state of the art, the other one with doping, the third one with copper deposition, and the last one with photocatalytic activity, so totally clear. Globally, I think, I also agree with Valerie saying that it's a really complex system, because you have 2 kind of doping and 1 surface deposition, and this kind of surface deposition is not so easy. It's not a mono deposition, let's say. So it's a complex system, and we still have some parts to understand to understand each part of this complex system. So with 3 parts, it's more complicated. The material part is really impressive. Lots of study on material, and you have a complete characterization of your materials with a lot of experiment. And I think that one really important point, because we really know what kind of material we have. XRD measurements, XPAs, a lot of experiments. The photocatalytic part is not so easy. We will talk after, because carbon dioxide reduction is not the most known photo activity, but it is really, I think, the important part now in photocatalysis. What is a little bit missing for me is more an analysis part and photocatalytic mechanism. We don't have any explanation on why this compound is more active than the other one, explaining with mechanism, but your system is really complex, so difficult to understand. We will go more in detail in this part after. First question, now that you have 3 or 4 years after of work in this area, do you think we will solve the CO2 problem of the atmosphere with your material?
No. 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 Not yet.
Why?
Not yet. It's so, if we want to solve it directly, you have to consider all the cost gonna take. And so far from the cost we take from to prepare catalysis and to establish all the test bench, everything's more cost than for CO2 reduction to methanol, because methanol also cheap, so it's not worth it. So far from this point of view, it's not worth it. And even though this methanol production so far is a good value from literature reference, but if they compare with some industry level, it's still quite low.
So, yeah, so the first problem of economic, it means that it's too expensive, but also maybe the amount. No, it's you cannot treat a lot of carbon dioxide with.
Yeah, so actually, even it's also a long time of issue for photocatalysis. The conversion is really low. Even like if you try everything to do for CO2 reduction, but still the conversion CO2 is low. But so that's why we just focusing on the absolutely yield of our products.
Okay, but we have to continue in this way. It's still interesting. You have to tell us, because yes. Okay, so your work is starting with some previous work at the laboratory. As Valerie mentioned, we could have worked only with one kind of doping, one kind of surface modification. But you choose one doping with one metal, one doping with the other, with non-metal, and one metal at the surface. Can you explain me, because you mentioned it a little bit in the text, but the choice of this kind of the element you choose? Niobium, copper, and nitrogen.
Yes, for the as I mentioned, just mentioned, the original desire for design this catalysis was we want to modify TiO2, try to improve its light absorptibility. So the directive way is working on its valence band and the conductive band. And for the conductive band, it's better choosing metal doping to generate a new VB and for a new CB. And for non-metal doping is to generate a new CB, a new VB.
I understand the principle of each one,
Yes.
but
Yes.
why niobium and not chromium,
So
for example?
So niobium for me, there's two reasons I chose. One is from previous work, so we already have a base for this to doing this. We know we can doping quite high concentration, and the second one is because niobium it's a radium atom, it's close to titanium. That's why it means it's gonna be easier to achieve substitution doping. That way can maybe gonna be easier for modification of CB. And for nitrogen doping, the nitrogen I chose because
sorry,
yes.
for niobium, for example, I understand your point, but it's close, but it's niobium 5. And for example, chromium 3 will be close also, but it's not the same kind of doping.
Niobium 5, we take 5 because 5 is more stable than 3. So it's for when we do the manipulated it, when we do the experiment, it's gonna be easier to do. If it's gonna 3, if it's niobium 3, it's gonna be more activated. So it's
I didn't talk about niobium 3. I mentioned chromium 3, for example, for other kind of doping. But you choose niobium 5.
Yes.
Okay, so only for because it's quite easy to substitute.
Yeah, because it's ionic iridium is close to titanium, so for niobium 5, it's gonna be easier to substitute.
Okay, okay, nitrogen.
Okay, for nitrogen here I choosing because it's really common for common in the reference.
Nitrogen.
Yeah, everybody knows nitrogen is good.
Yeah.
And nitrogen, so there's a lot of reference outside, so it's gonna be easier to. And for me, I chose nitrogen also because nitrogen is gonna be more clean than sulfur or or other element. For me, nitrogen is more close to carbon, so it's a more environmentally friendly than other elements. So, and for nitrogen doping, can also choosing different kind of method to achieve. So that's maybe it's a reason why I chose in nitrogen.
Okay, okay, and copper. Copper is not easy. Why, for example, why didn't you choose platinum?
Platinum is good good catalyst for every reaction. For for platinum, it can catalyze every reaction. So, but it's expensive and it's rare. So, but they always try some not expensive non-noble metal to replace platinum. And for copper is cheap and copper is easily to obtain. And for copper, especially because it has the ability to construct the copper bond and the copper hydrogen bond. So when they're loading copper, they are all more easily to obtain the copper 2 plus product. So that means it's a greater chance to obtain more value-added product. But there's a way because there's also a problem for copper. The selectivity is difficult to control. So even though copper, so this is the long term for in the reference. They try to control different kind of copper to improve its selectivity.
Okay. So your idea was to use copper to obtain the oxidized form.
Yes.
Yeah. Okay. Because and because it's cheaper, and also because but it is really more complex because it's you don't control exactly what kind of you have two forms of oxidized form.
Yes.
Okay. Okay, so also okay, so for this system, I try to I can understand. So you choose this kind of system first. You made the doping directly on the aerogel. So also you didn't work directly on the elaboration of the aerogel because you used a method already developed at the laboratory.
I'm sorry, I didn't follow the question.
I mean that you choose one kind of aerogel. I suppose that your aerogel method was already made at the laboratory.
So you reproduce all results.
Yes.
You never develop an aerogel.
From a reference, there is for niobium dope and nitrogen co-dope the TiO2 aerogel, but for loading copper using our for in situ method and the gel synthesis, we already add copper and we can send it to obtain really small particle. This one I think is original.
Okay.
Yes.
Okay, so you choose aerogel method. It means that you made a sol gel, and then you dry it by supercritical drying under CO2.
Yes.
The idea was to keep a monolith, or you wanted to obtain the powder.
I'm sorry, just the connect is bad. I didn't hear the question clearly.
When you prepare.
Sorry, Christophe.
Yes.
I will just at the end of the critical step, you obtain a zero gel,
yes,
a powder, other. What you obtain? What is the texture?
After aerogel, after we supercritical dry, obtained was bulk. Then we grinded to powder.
Okay, but the idea that you prepare first a gel.
Yes.
And then you dry it.
Yes.
Your objective was to keep a monolith form, or just to obtain a powder?
Yeah, at the beginning, it's to obtain the powder.
Okay, so can you explain me your process to make the aerogel? You replace the alcohol containing your gel by the carbon dioxide?
So here we, the beginning was using solid gel method with mix the titanium sauce and the dopant with water and acid inside to synthesis gel. And after gel was aged, and then we use the supercritical dry to obtain the aerogel. It's to evaluate it. It's a solvent, isopropanol inside. So in that way, can take off all the solvent in the short time that we can keep the pore size and didn't get the shrink of TiO2. That we can get aerogel.
Yeah, I understand the principle, but the realization of an aerogel is not so easy. And you can have some continuous drying or some batch drying, for example. Can you describe how you make it? Because you have to take the alcohol of your gel. So you can make it by liquid exchange, with
Yes.
liquid carbon dioxide, or you are always in a supercritical condition? It's not clear. My question is not clear.
So sorry, I did not completely follow.
Can you
So
can you
at the end,
can you just
you obtain a gel,
Yes.
okay, and after that you put your gel in solvent,
Yes.
yes,
Yes.
and it is for one batch. Yes,
Yes.
it's not continuous.
Yes.
Yes, it's step by step.
okay, step by step? I mean, one autoclave, you put your carbon dioxide.
Yes.
Yeah.
Okay. And you obtain at the end your, but okay, I don't know how the alcohol is getting out.
It's during after we aged our gel, and we're gonna do solvent exchange to replace the water and acid inside, to replace everything, to make sure all rest was all isopropanol, all was alcohol, to make sure before we're doing the supercritical dry, there's no water inside.
Okay, after the aging.
Yes.
Okay. So you obtain your aerogel, and then you make a calcination step.
Yes.
I mentioned 550 degree.
Yes. Our calcination temperature was 550.
Always. Why did you choose so high temperature?
This temperature choosing because this temperature we can get in a good crystal structure. At the same time, it's not too high to obtain rutile, but and we also can get a good anatase structure. If the temperature is too lower, like 500 or 400, the crystal structure, the crystal line is not good enough. But if gonna too high, we're gonna get in rutile and agnatase phase, both mixed. But maybe mixed phase was gonna be better. But the system, the catalysis system is already complicated enough. So I want to try to use this as single crystal structure as much. So that's why I chose this temperature.
Yeah. I understand that you cannot go higher because you will have some rutile form, but 450 or 500 will be better, not to keep enough surface, and you will have a good crystalline quality.
Maybe in the aerogel, if you lower the calcination temperature, the SPT gonna get it higher. Yeah, it's a so it's good advice to see. Maybe lower the calcination temperature gonna get it higher SPT, and meanwhile we can keep anatase phase. Yes.
No, because I think in this kind of system, when you make you have your aerogel after your drying, but you need a calcination step to crystallize and to burn all organic compounds. But I think between 450 and 550, you have a good window, and sometimes it can be better not to go so high than 550, and you can keep more surface at 400. No, you didn't. You already made your calcination at 550.
Yeah, it's like at the beginning to try to make sure because it's already complicated enough to make sure others condition gonna be as same as much. So to try not to change it.
Yeah. That was my first question. You use a recipe of your laboratory. You didn't change this parameter because this kind of gel was okay. Okay.
Yes.
Okay. Okay. Let's. Can you show me the slide 18? Because let's talk about doping. Yeah, that was okay. In this one, you mentioned that there is no change in the light absorption even with doping. I think you mentioned it. You say that there is no change in the band gap in this case.
Yes, so even though the spectra showing there is improved in the visible light, but from after we obtained the band gap, it didn't show a clearly decrease. So the band gap didn't decrease, but from the spectra we can see the light absorption ability is improved.
Okay, because you mentioned that I see on your slide, improve light absorption. What you called improve light absorption in this case?
And it's from the visible light, it's the light absorption it's increased, and from 300 and 400 there's because niobium doping there is a redshift, and this also can improve the light absorption. And from the spectra, you can see the spectra is getting higher than compared with P25 and pure TiO2.
So what you call improving light absorption is that when it absorbs more visible light.
Yes.
Okay. That's with the question of Valerie of your spectrum of your light. It's because you have a quite continuous light. You mentioned xenon light.
Yes, in the experiment I use in the xenon light. It's a full spectrum.
Okay, and you think that if you absorb more of your visible light, it's better for your activity. That your idea of improving light absorption. Okay.
Yes.
Even if the gap is not changed. Okay. Okay. So concerning the, can you show me the same picture with copper? Okay, so that was the question. Not this one. The one with the band gap.
This is the band gap. This is not showing table, but showing the with arrow bar, but in the figure, the right figure.
Okay, so that was the point that mentioned Valerie, I think, also on the point that you have absorption of copper oxide. Yes. So you cannot say something about the band gap. Okay. Yeah, I wanted just to mention that I will avoid Kubel-Kamunck calculation in this case.
Maybe it's risky to say it.
Yeah, more than risky. I think it's not true.
Okay.
Because you can show this absorption, but the assumption of the calculation of Kubel-Kamunck is only with one band gap. So I think you're more than risky. It's false.
Yes.
Okay. Can you show me the picture, the microscopic picture with copper? Yeah. Yeah, that's it. So, can you sum up exactly what you make a very good characterization on that? So we have titanium dioxide, we have copper monoxide, copper 1, copper 2. There is no more copper?
For copper, the most
copper.
Others are gonna be the metal copper 0. But from what we observed from TM, I didn't see that thin lattice of copper 0. It's gonna be really, really thin than the oxide did, but I didn't see it from TM.
So how can you describe you have your titanium dioxide, niobium and nitrogen are inside.
Yes.
You prove that it's a good doping, really a doping and not a modification. And then at the surface, you have at the same place one big metallic copper with a small island of oxidized part. How can you describe your particle?
It's copper. It's loaded TiO2. This is one piece of TiO2 on the base, and there's a copper one, the copper 2 oxide insert in there in the TiO2, and that's why it's because the TiO2 is mainly gonna be mainly showing in the TM. That's why its lattice was easier to see. But these two, it's just because this one is getting lucky to see two at the same time. But usually they are separated. It's in different place to measure, and yeah, sometimes it's not always getting the stay stand together. Sometimes it's separated. Sometimes it gets together. So we calculated as just as copper oxide species, not gonna say one specifically. So yeah, it's because it's a state, it's a mixed. It's difficult to say which one is which. So we can just say a cuprous or a copper oxide species, not just one.
Okay, because the idea is to try to understand the mechanism of your CO2 reduction,
Yes.
and when you make the photoactivity, you are eliminating your titanium dioxide. We are creating charge carrier electron and hole going at the surface and generating some reduction and some oxidation.
Yes.
Okay, so you need to reduce your carbon dioxide and to produce your methanol. You mentioned and you thought that on pure titanium dioxide there is quite no production of methanol.
Yes, low. It's not a no, but lower.
Yeah, but as mentioned, Valerie, I'm not sure without blank and with no carbon species inside. So I think that there is no possibility to make your reduction at the surface, even with doped compound, because it works a little bit better with doped compound, without metal at the surface. You need the metal at the surface to make your reduction. Are you okay with that?
Yes, it's have to, because it's a solid gas system, so the reaction was occur in the surface of catalysis. So have to be absorbed first, and the reaction gonna happen in the surface, and then it's gonna absorb.
Yeah, but something is getting in the metal, on the metal surface, not on the titanium dioxide, on the metal.
Yes, some of it happen in the particle, not metal particle, metal oxide particle. But even without loading copper, one of our catalysts, even with doping, it's also getting good effectors. That means even pure TiO2 also can get a good. Yeah, this one. Just after modification, it's improved the light absorptibility. That's why already gets a good methanol production, and copper is just another way to improve it. But they both good for the reaction, but in different kind of way. So yes.
Can you show me the other part? Yeah, in this case you're right that you have quite the same with the only doped one, but I think the copper plays really an important role on the reduction, not on the photocatalytic part, because you have some light absorption and creation of charge carrier. It's happened in the carbon dioxide and the titanium dioxide. But then you have some reduction step on the metal.
Yes.
But it's not. But if you don't know exactly, because in your case you have the copper and the two kind of copper oxide and the titanium oxide, so you can generate maybe some charge carrier in the oxidized part of the copper. So that was the idea when I talk about mechanism. I would like to understand exactly what happened. Do you have any idea?
This I can just say copper can improve as it exists as co-catalysis. That's why it's getting important role compared with doping. And yeah, doping was in a way to improve the light absorptibility, and the copper was exists as co-catalysis. Maybe copper also just even without doping, just loading copper already getting a good catalysis performance. So that's why it exists as co-catalysis. But some of the reaction was happen in the copper oxide the particle surface, and some of the one on the TiO2 surface. And with loading copper, it can improve the light, the electron transfer efficiency. That's why the catalyst performance even getting higher. Yeah.
For me, you have to divide in different steps. The first step is the absorption. You talk about the absorption first, and you said improve or not. Okay, you have to absorb your photons, and this happens in the titanium dioxide, and maybe a little bit in your copper oxide. It's not clear, but maybe it can be. Charge carrier are created. You have a lifetime of charge carrier. They have to go at the surface, and then they are making the reaction. At the surface of pure semiconductor, you can oxidize some species, but the reduction is not so easy, and I think you need the metal. You're right in your case that you have one case with niobium working without metal, but I think you see that with copper is working, because the last step of the reduction is for me on the metal, and I think it will be interesting to try to understand and to make this kind of mechanism to understand exactly what happened at each step. Okay, you understand?
Yes.
And I think it should be an interesting discussion to understand what happened in your activity, and it should explain why your compound at the end is this one is the best. Okay.
Yes.
Because you talk a lot about surface area, but I think the surface is not so. It's one important point, but it's not the most important point in the case of activity.
It's for me the design we use in high specific areas to improve to how to absorb CO2 on the surface. Gonna be easier for the reaction going. And for our case, TiO2 aerogel, pure TiO2 aerogel already getting like same performance with P25, and P25 is commercial catalysis. So we already have a pure TiO2 with anodized phase already can compare with commercial catalysis. So we think that SBT, higher SBT already working, already showing their work in our case.
Okay. Okay, just okay, but thank you for this discussion. But I think it is important to mention all this part. Show me picture slide 44 and 45. Just. Can you hear me?
Yes.
Yeah. Just 45. Yeah, so I think we already mentioned this, that the comparison is really different because you don't have the same light, but also you don't have the same reactor. So I think that we have to talk about standard in this case, and I think you cannot. It not only because of the light. I think also because of the shape of the reactor. In your case, for the just one before the 44, can you explain me this point with temperature? I didn't understand everything.
Here is for a bubble system, just pure CO2 and to bubble in water, no addiction, no other addictive stuff. And the first one, the 0.3 was the reactor with CO2 and the water, but in the room temperature.
Yeah.
And then because we think the methanol production is quite low, maybe because the temperature is too high, CO2 is just above the water. It didn't dissolve in the water. Because from the trend we can see with the temperature increase, the solubility in water is decreased. So here we continually the reaction, but we lower temperature to 50 degrees. In that way to increase the solubility of CO2 in water. And that way actually it's also we can see even pure purged CO2 we're getting a higher methanol production. And that means our design was correct. It's because CO2 solubility. And then we want to try to more improve to prove that. So to say it's mainly because CO2 solubility in water to affect the performance. So we added the sodium hydroxide. This base gonna absorb CO2, a lot of absorbed in the water, and even we can see with react in the low temperature, it's still getting a good methanol production. And then with this solvent, we higher the temperature to 60 degrees, and but in here our catalysis was dissolved in this temperature. It's an interesting finding, and but this value is not reliable because catalysis was dissolved. And then for the 5, we have to compare our reference, so we added a methanol. We added a new sodium hydroxide with new catalysis and react in the room temperature to compare with the reference or with the one the last system we did to see after improve the solubility in water and the methanol production is improved significantly. So this to improve the system choosing is really important for CO2 reduction.
Okay. Okay, but what I don't catch is how could you make so high a production of methanol if your catalyst is dissolved?
This one, this is I take the liquid at the beginning. After I finish reaction, I didn't see the catalysis was dissolved. I just take the liquid directly, and then after I want to recycle my catalysis, I see from the reactor, the solid was all gone, just liquid. There's no more catalysis in there. So yeah, so from there I realized that this value is not reliable. Yeah.
Okay. You meant.
Yes.
Okay. So I think we talk a long time. I just thank you for this discussion, a very, very interesting scientific discussion and results. And congratulations for all this work and all your interesting results. I hope you will have a lot of publication with that. Maybe, yeah, you already mentioned something. So, okay, so thank you very much, and I let you. I give back the the discussion to the president.
Thank you so much, Christophe, for the nice discussion. So before to give the floor to the local member of the jury, so I will ask you some question also.
Okay.
So I share the point of view of my colleague regarding the manuscript. So it's really clear, it's well written, but sometimes it's difficult to understand because a lot of results, a lot of materials. So, and probably the most difficult is to try to understand the effect of each compound, because there are many in the same material. So sometimes it's difficult to understand what's happened. And I have maybe I have some question also about sol gel, because my lab is a pioneer in sol gel chemistry. Okay. It's a Jacques Clivage lab, so I have a long past with sol gel. Okay. And will I come back on the reaction? Okay. You mentioned in your manuscript, page maybe 56. So you mentioned some hydrolysis and condensation reaction. Okay. 5-6. Yes. Page. Okay. So we give some reaction. So you give some equilibrium. Yes. You can go at right or at left. In your opinion, what is the most relevant sense of the reaction? Is it really reversible or not? And in your case, what happened? So, for example, picture 123. Yes. You have the hydrolysis in one sense, and in the other, esterification. Yeah. Yeah. So theoretically, it shouldn't be reversible. But theoretically, okay. Yeah. And now, experimentally. Yeah, experimentally, even in the same condition, I think so from my experience is if it's gonna become gel, it's become gel. Yes. In fact, both reaction is possible, but it depends on the metals, of the nature of air, and it depends also of the solvent. So it depends of many different parameters. So yes. I think it's difficult to keep like that, because it's too general. I think too general point of view. Yes. In your introduction, page 47, you describe the loading using a metal. Yes. And you give the different reason for the improvement of the catalytic activity. So you speak about stocky barrier formation. Yes, I agree with that. And after that, you discuss also about electron sink property. Yes. Yeah. Is it two different mechanisms, or is it due to an effect to cause a relationship? So, because for me, it's possible to store some electron due to the stocky barrier. Is it? This should. Are you agree with that? Or? Yeah, I agree with it. There's two at the same time. Should be one is the Scotty barrier formation, new Scotty barrier formation, and then the electrosync. At the same time, it's not just separately. But because that is segregated, it's working at the same time. They both, if you're loading with a noble metal, it's gonna working in this same this way, this two way at the same time. Okay, the two effect is linked, in fact. Yes. Yes. Okay. Thank you. Yes, about aerogel formation. If you compare to nanoparticles, what can you say about cost production between both? And actually, I don't know exactly what is the maturity of supercritical drying.
Yes, this something I was worried. Actually, it's worried in the beginning. It's it's not quite expensive, but it is. It's gonna quite cost a lot. No matter from a supercritical dry, you're gonna how much CO2 gonna using, and during the synthesis, how much electron gonna using and everything. But after that, the only thing will produce from CO2 is low conversion, but and getting methanol, and yeah, the cost is not balanced.
And regarding the quantity of powder you can treat in same times. I think now it's increased a lot.
Meaning for supercritical dry,
the minimum quantity of materials you can dry in same time. The size of the reactor, for example, because I think in your lab you have a small one.
Yes, from the lab is like this, so not too much.
What is the quantity of materials you can dry?
Dry at the same time,
reactor?
I think it's gonna be 10 gram or 20 gram like that at the same time. Yeah.
Okay. It was just a question because
it's ours is a small reactor.
I have all information during long time. These techniques was limited by the quantity of materials, but I think now the techniques is really improved and nice. Okay. From chemical point of view, have you an idea of what is the effect of the supercritical drying on chemical reactivity? I mean, for example, maybe we have some residual alkoxide group. Have you looked at if all the alkoxide are completely hydrolyzed or not?
This is I'm not sure. the formula I'm
what
using.
Technique, what kind of techniques you can use to see if there are still some hydroxide?
It's all you can see from after every time we change the solvent, we keep the solvent that changed to then to do EDX or ICP to see if it's the residual titanium or other metal inside, or just the pure acid or something.
But you can simply use some infrared spectroscopy to see if there are some residual alkoxide group. Because you're starting from butoxide for titanium and propanol, isopropoxide for niobium. So maybe there are still some carbonic group.
Yes.
And I ask you this question because when we are looking at the color of the materials in page, I don't remember it's 9.7. So after calcination in air,
yes,
it seems to be white. So the color is not probably good. It's sometimes
no,
blue. And is it white powder?
No. It's I don't know. It's maybe because of phone or the day I was shooting. Actually, it's from the berry eye to look. It's yellowish.
Under air?
Yes.
Yeah. And after calcination on ammonia,
and
it's still gray.
Comparing the air, it's still yellowish, but more grayer.
More gray parts. So, and as Valérie already told you, maybe it could be due to residual carbonic group, because when we burn in air, so you make the degradation in CO2.
Yes.
But if we don't have enough air, in sometimes, maybe on N2 also, when we make the calcination on 2 also, probably you can see some residual carbon atoms at the surface. So maybe it could be due to the residual groups. So to be sure, you need to see if there are any groups, hydroxide groups, after maybe before supercritical drying and after. But you can use only very simple spectroscopy to see that. Okay.
Yes. Yes. It's a.
If you are looked at by infrared spectroscopy, you can see these different groups, so it's quite easy to do.
Yes.
But it's really important because we see some effect of the calcination under ammonia. And sometimes when we are look at the quantity of nitrogen in the materials, it seems to be difficult to say it's only due to this very, very small quantity of nitrogen.
Yes.
For example, I think we have some XPS. I will try to retrieve the slide. Can you retrieve an XPS? Maybe slide 12. No, it's no, I don't think it's this one. No, slide 15. Yes. Oh, sorry. I look at my paper, not your slide. So yes, here you say it, so the we observe a shift of the peak. Here, yes. Just when we put only nitrogen. But do you think it's possible to see this shift? And you say in your manuscript that the quantity of nitrogen is very low. I don't remember exactly the value, but it's 1.2, 1.3. I don't remember.
It's nitrogen compared to oxygen. It's 0.7, but 10 minus 3, 0.00077.
Yeah.
Really, really low.
Yeah. Do you think that the small quantity can be induce such of shift in the XPS spectra? Is it possible to observe this shift with the small quantity of nitrogen?
Could be. So it depends on the detector sensitive. Maybe it's a slow, even just a slow, a little bit, the electron density is change, maybe gonna shift. But yeah, but for here, maybe also because of oxygen vacuums. For the surface electrostructure is complicated to say. From here, the only reason I compare with no nitrogen doping, the only reason change for its nitrogen. So here I think it's due to the electron transfer from nitrogen to titanium, and also maybe could be from ammonium reducing effect. It's generated titanium-3. Also could be, but in our case, I cannot to separate the titanium-3 from in my spectral. So maybe in that way, it's showing in the shift, except but not new species.
Okay, maybe. Is it exist some calculation of such spectra using some model, for example, to be sure of that? I'm not an expert in XPS, but sometimes it seems to be very strange because the shift is important, and you are look at titanium atom, in fact.
Yes.
So I think maybe there are another effect. It's not only due to nitrogen. It could be due to other. Yes, if I come back on salt gel chemistry, at the beginning of the chapter 2, yeah, you said the hydrolysis of titanium alkoxide is very fast. So you decided to catalyze the reaction.
Yes, using acid to, because for my idea, catalysis means you can speed up. You also can slow down the reaction.
Are you sure of that? It would be very
my idea.
Normally, when we make the catalysis, it's due to the low reaction because the reaction is very slow and the rate is low. So we will increase the rate of the reaction by catalysis. In your case, you say it is speed, but like you, so you need to be more.
Yeah, from my idea, I can also can slow down the reaction.
Do you think this could be also due because you add some nitric acid? So in acidic medium, you know that you can increase the surface charge because we have some protonation of oxygen group at the surface. Do you think it could be an effect of the repulsion between particles, for example, and to maybe to help to make the gel, because to make a gel we need to have some hydrolysis and condensation, but it is too fast. In sometimes you make some particles, and particles precipitate in the suspension. It is like in silica, for example, if you look silica hydrolysis in basic medium, so we see the precipitation of silica nanoparticles. But if we are working on pH, acidic pH, so we have some different condensation pathway, and we have long chain and less reticulation of the chain, so we have some gel at the end. So do you think in case of titanium you can see similar effect, in fact? So it could be easier to make some gel in acidic medium, probably due to the kinetic reaction of the condensation, due to the catalytic effect, because sometimes it's easier to make some condensation at the end of the chain compared to the increase of the reticulation of titanium atom, for example. So maybe you can look in similar chemistry, and especially using silica to understand, because I think it's
it should be similar as silica for gel synthesis. It can go as long as with condensation, it's gonna be a chain. The chain gonna be longer, and yeah, it's a similar mechanism.
What difference you see if you look at the formation of the gel? What is the main difference if we make the hydrolysis without nitric acid and with nitric acid? At this stage, you see the formation of white gel, or maybe transparent.
The color of gel after synthesis, I think it's, for my case, I don't know for others. I'm not really did a lot reference from here at But I see from the gel's color, it depends the solvent, the ratio of solvent and the ratio of water. And for when we change the formula, we increase the solvent and the acid and the water. That one I get its white gel. It's not transparent, and the formula I using is the gel we obtain is transparent. So I think it's the main difference gonna be solvent, acid, and the water. Yes, these three both working.
So maybe you can comment this part here, because I think it's not only a catalytic effect of hydrolysis, because it's really very fast. So we don't need that, but probably regarding surfactant effect and protonation and reactivity and kinetic of the different reaction, we can discuss about that. In the same page, 950, it's not always clear for me that for all aerogel are calcinated or not. Because in the name of the compound, so we said the obtained aerogel are denoted ATiO2 and BX. And after calcination R, it is the same name. So I don't really understand. And just to be sure, when we show some XRD, is always after calcination at 550 degree,
yes.
100 degree. Okay.
Yes, so here, so
okay. Because at the beginning, for me, the characterization has been done after supercritical drying. So I don't understand the generation of nitrogen starting from urea, for example. What is the mechanism of the degradation? So degradation is only due to the calcination, in fact, or not? Because we describe two different ways for nitrogen doping.
Yes.
Yeah.
Yes.
The first one, you use some urea.
Yeah. The one. Yes.
Yeah. And what is the mechanisms?
It's same like a copper. With at the gel synthesis, we already added the urea in the gel. So after calcination, during the calcination, it's gonna decompose the organic of oxygen, the such stuff we're gonna be burning out, and the nitrogen gonna stay in the lattice.
Okay, so that means all the characterization are done after calcination.
Yes.
Okay, but sometimes it's not so clear. Yes, we will come back on the size of the particles. So you give some value coming from analysis of same image. So we find 20 between 20-25 nanometers in size.
Yes.
And in slide 54, I think, you show this slide to when Valérie asks you some question. Here you give some size from XRD. 5.4. No, it's no.
No.
No, yes, it's no. Yes, it's this one. So here is the size coming from the analysis of XRD.
Yes.
So you determine the broadening of the peak. Okay. This value is related to only the first one, the first peak. In
the 101.
Oh, okay, okay. Yes. Cool. Maybe it's better if we can make
others to compare.
Yes, maybe 5 is good.
Okay.
But on 1 is not so. Yes, it's not enough. So we need to be sure its value is the same if we are looking different peaks. So probably we have some. I know for Anatas it's not so easy because there are several peaks at the same angles. But if we are looking at between 45 and 50. Degree, so we have one, and maybe you can try to make the deconvolution of the two following between around 55, for example. So you can try to find it to make the deconvolution of different peaks and try to have almost 4 or 5 peaks. And now if I look this value, how you can explain the difference between the size of the particles determined using CM and this one.
But this one it's a crystal size.
Yeah,
it's crystal size, but if the crystal size not determine the particle size.
So you mentioned in fact it could be due to aggregation, and we can see in CM an aggregate and not a single particles. But it could be also due to core shell particles with crystalline core and amorphous shell.
Yes.
So I don't know, probably if you are looking for TEM particles, if you come back on TEM image, yeah, using this image, maybe you can conclude. Yes, for example, here it's difficult to know where is the titanium dioxide. Probably, yes. If we are look the big one at the center of image A, yeah, it seems to be more than 20 nanometers.
Yes.
Yeah. So now you need to see if there are some crystalline plane to be sure is it one single particles, one core shell particles, or an aggregate of with 2 or 3 different particles. Okay. Because it's I think it's important in your case, because I don't really understand the great variation in surface area compared to the size of grain. In fact, the size of particles. How you explain the variation of surface area? For example, if you look for niobium, I think I don't. Yes. Page 112. When we put one, I don't know, yes, 1% of niobium, so you see a strong increase in surface area. Okay.
Yes.
Yeah. And in fact, the particle size, it seems to be the same.
For the crystal size, it's basically the same.
Yes, and for particles, you determine using CM. There are no great difference between all the particles. It's yes. If you look at maybe page 110, you have 4 different values. But if we look at the uncertainty, it's exactly the same. Okay.
Yes.
Okay. Yeah. Okay. So how you can explain so the increase in surface area? Have you looked isotherm, because we don't give the picture of the total isotherm. Have you? Yes, you make it because you give some pore volume. So do you remember the type of the isotherm? Because we have some porous materials.
Yes.
So you know the different type of isotherm for porous materials? You remember
Yes,
you or not?
5.
Probably it's type of 4. No.
It's the one with misopo.
Yes, like that. And when we come back,
Yes, there's gonna be space between.
Yeah. That means the porosity is due to the cavity make from an assembly of particles. Okay. So it's interstitial porosity, intergranular porosity. So probably that means the porosity and air increase. Okay.
Yes.
So I agree with that, but the surface area increase also. To increase the surface area with an assembly of particles, you need to decrease the size of particles. So it's difficult to understand why is the surface specific area increasing in this case. You speak about maybe defect, surface defect. What is your opinion? What kind of defect it could be? But what kind of defect could be increase the surface area?
For here, I explain it as particle size decreased. Yeah, it's
because in your case it seems to be significant. So this is increase, and we retrieve the tendons. It seems to be correlated to nobium also.
Yes.
So maybe it could be the rugosity of the surface. Maybe. So if we have some TM image, maybe can try. I know we don't have this observation for many samples, so it's difficult to see because it could be due to the rugosity of the surface.
Yeah.
And in case of nitrogen doped materials, you see a very strong effect. So the rugosity also can be due to the calcination and reactivity of the surface on ammonia atmosphere, because probably there are some difference between the two different calcination and the two different atmosphere, in fact. Yes, if you come back on slide 36. Regarding the improvement of the catalysis with the different materials, you can come back on slide 36. Yeah. Yes, I think the discussion with Christophe is very interesting. So if you're agree, maybe we can continue the discussion. When I look your result, so when we increase the quantity of nobium, so the quantity of copper at the surface increase also. Yes?
With no in the nitrogen. In the nitrogen, the copper one content is increased.
So I'm trying to make some correlation like Christophe to understand. And yes. When you are looking your result page 138, using XPS, you see an increase of the quantity of copper for the two last sample.
Yes.
Nitrogen and nobium and nitrogen.
Yes.
So can you say that the increase on the reactivity here is due to the increase of the copper, the quantity of copper at the surface?
It could be because all of copper was getting more copper in the surface, and that's why the copper one is getting higher in the surface. Yeah, maybe that's due to that with niobium, the more copper in the surface and the performance is getting higher.
Yes, it could be interesting to try to normalize the results regarding the quantity of copper to see if there are some synergy. When we are looking at your materials, you have copper, nitrogen, and nobium, and maybe you can try to make some small calculation and try to normalize to one quantity of materials to see if there are some synergic effect of only additional effect also.
Yes.
Because it seems to have some difference when we make the calcination under NH3. And maybe also here you see some great difference in the quantity of copper at the surface, because in fact we don't know exactly where is the copper, because in some samples we have some copper, but less at the surface. So maybe you can have some interstitial copper inside the TiO2, because it's not only, it's never copper zero, or it seems to be never copper zero. And if we have some copper 2+, for example, or copper plus, maybe you can have also copper inside the materials and not only at the surface. Here, the result is very interesting. So we see a kind of rejection of the copper at the surface when we increase nobium inside the matrix.
Yes.
And regarding the copper, how you can explain the reduction of the copper? What is the chemical reactant, the chemical reductant, in your opinion?
For reduction of
because
copper.
you at the beginning you put copper 2+. Yes, because we start from nitrate.
Yes.
Okay, so at the end you see some copper plus.
This is copper 2 sodium, nitric sodium. It's to oxided to copper cuprous and the copperous, and this is a very typical reaction for copper oxide. Because the energy needed to oxide to these two species, basically it's not huge huge gap between these two, so it's really easily for even.
Yeah, I know it's really easy, but what is a compound you can make this reduction?
So for copper, you oxide from the beginning to calcine it. It's always get these two, so it's difficult to distinguish from each other.
Could this be due to alcohol? Because at the starting you put some copper nitrate in alcohol medium. So in some case, for example, for ruthenium, we see when we mix ruthenium 3+ or 4+, I don't remember exactly, in soluble solutions, due to the large quantity of solvent and organic species, you see a reduction of the ruthenium. When we increase the quantity of ruthenium at the beginning, it stays at a good oxidation number, but when we increase the quantity, we observe at the end a reduction, probably due to the alcohol or maybe to the alkoxide group in the solution. So do you see a change in color of the solution when we put copper nitrate inside the solution? I think it's A, the solution A. You mixed your different alkoxide.
It's showing the really typical copper 2 color, the blue.
It's blue color.
Yeah. So all of this was even after age, it's decent change. It's still showing the copper 2 colors.
There are no change in color during the aging of the solution.
No, it's just they remain like this even after supercritical dry. So.
And when we mixed A and B solution, there are no change in color.
No.
Okay. But it cannot happen after, maybe during supercritical drying, for example. So you see a change in color after and before supercritical?
No, it's still showing
it's only after calcination.
Yes.
Okay. Okay. I have another question about impregnation process.
Yes.
So, in fact, in your case, you use some weight impregnation.
Yes.
Yeah. So that you put the samples, the solid, inside a large quantity of solution.
Not large quantity. It's basically the same volume as the solid, and measure the basically same volume of the liquid.
At the solid.
Yes.
Yes. I think in my lab we don't put the same quantity of the volume of solid, but the same quantity of the volume of the porosity. Yes, because in fact we try to put the solvent inside the porosity. So we make the calculation because we have some value of porosity of pore volume. So we add exactly the quantity corresponding to the pore volume, in fact. So maybe we can look at some catalytic paper regarding the preparation of supported catalyst using some impregnation. So maybe it's too much in your case. And probably it's because we see some we have some pore, and we speak about accessibility of the pore due to the presence of copper oxide particles. So maybe it could be due to the quantity you put inside. So. Okay. So I think a last question about the effect of the temperature when we are looking at the activity. Slide 38.
Yes.
Yes. Yes. If you analyze this result, what is the reason of the increase of the activity? Is it due to a better in some time when we increase the temperature, you improve the probability of reaction because we have more thermic agitation. So in your case here, how you can explain the increase of the activity? What is the step of the catalytic reaction that could be improved by increase the temperature of the test?
From my perspective, I think it's increase of temperature. It's from thermal. From thermal this perspective, temperature increase, so the molecular movement gonna be increased.
Yes. Yes, it's due to the probability to
the molecule connect with the
connect with them and the mobility, and you increase the mobility and you increase the elastic probability to make some reaction.
Yes.
Okay. And regarding the solubility, how you can I will try to determine how the solubility vary and with the temperature.
This is for sodium carbonate system because we using this sodium as a base of in our solvent. So solubility should be avoid. It's not a problem we can consider in this system. So from here, temperature not gonna do a big effect for solubility of CO2.
Okay. And regarding absorption, desorption, have you seen something?
Yeah, if like temperature getting higher, it's gonna be easier to desorption for molecule away from the surface. And so yeah, in that way also could be improved the catalyst.
Okay. Okay. Thank you so much. And congratulations for this nice work.
Thank you.
So now the easy part of the discussion, the more.
Thank you.
Yeah. So I give the floor to Arnaud Rigachi.
Merci, Corinne. So thank you very much, Miao, for all these years altogether, first of all, and your presentation and also your manuscript, because it was, as already said by the three experts, external experts, very clear, very well structured, and very well documented, and also very interesting, because a lot of results. But this is your style. You want a lot, and you go directly to the objective. And during these 3 years, you work very, very hard with a lot of papers to come, I guess. I hope so. Okay. So I will be rather short because all very, very, very interesting scientific discussion I've already now, I would say, long as 2 hours, so maybe you are exhausted. So I am just going to say some words about aerogel, because I've got a couple of comments and questions. It is so interesting for sure. And as an engineer, I would say. So the first thing, it's a very general question. Can you tell us again why using aerogel materials, which are difficult to synthesize because the processing route is very long, because precursors are costly and expensive and so on. Why using this instead of suspension of nanoparticles?
So it's from at the beginning, from design the catalysis, and we take advantage from our lab. So it's already they have a rich experiences in synthesis aerogel, and they know how to apply it. So, and this is also a new material for me the first time to learn. So it's also interesting material to learn. So after I find it have a really higher porosity and a higher specific area, so maybe it's gonna be ideal catalysis for us we can take it directly, and we use this kind of morphology to use into they're gonna pour, they're gonna high porosity, so we can get a more place to absorb CO2 molecule on the surface in that way, because this is the first step for the CO2 reduction. And in that way can directly improve, because also we also compare with some result, our SBD with some result on the reference. We also have a really good performance compared to those on the reference. So that means at the beginning our design was achieved, and then from our catalysis performance, our pure TiO2 anatase phase already have comparable to the commercial catalysis. So it also means our design was success. So at the beginning, our using the take advantage from TI aerogel, it's also a success. So it means it's a good choice.
No, thank you for this. But what I mean is that finally the specific area of nanoparticle, because of the size of the nanoparticles, something rather high, even if it is lower than the aerogel materials. The volume, the porosity, so to say, when you are talking with a suspension of nanoparticle, finally it is not really a problem because of the volume, the porous volume, so to say, is the volume between the nanoparticles. So I guess there is something more than the internal structure and not texture, because, okay, I don't know what is a good word. Structure, it was chemistry, texture, it was characterization, internal morphology. So I am going to tell about texture. I guess that I think that the continuity of the solid network is also something that is very strong regarding the suspension of nanoparticles. Because of the contact between the particles, the intimate contact, the covalent contact between at the neck of the particle. So I guess this could be something. And another point, do you think that working deeply on the temperature of calcination could permit to make coexist rutile and anatase? Maybe it is stupid, but when we are comparing to a product, this product is P25, this is a commercial reference, it is very efficient and so on, and it is something, it is a mixing of anatase and rutile, but without any contact except the Brownian movement of the particle and so on, but no covalent contact. Do you think we can take advantage of this? Or maybe it is completely stupid and we have to work with pure anatase and do not work deeply on the temperature of calcination. What is your feeling about that?
My opinion is, beginning, I chose this because as we already discussed, just my catalysis system already complicated enough. I don't want to introduce another
coming tests.
Yeah, so the more factor gonna influence in the catalysis performance, more factor to analyze. But from the literature, from the paper already read, the mixed phase with anatase and rutile, they're gonna getting higher performance, especially in photocatalysis. So that's why the P25 is commercial catalysis mixed and it's get good performance. So in my case, maybe we can change the calcination temperature to getting the mixed phase both, maybe getting a higher performance. Yeah, it's good potential.
Okay, thank you for this. So I'm going to be short. Don't be afraid. Regarding the characterization of your materials, you deeply characterize XPS, chemistry of surface, EDX, M, TM, and so on. But there is a basic property which is lacking for as far as I'm concerned. It is a density of the materials. Okay, we can say that photochemistry is not directly linked to density for sure, but at the second order or the third order of interest, I have the feeling, you're reading your manuscript, that it could be of interest to still optimize. For instance, a question regarding porosity. You have used the absorption of nitrogen, which is a very valuable method for sure. You have applied the BGH treatment, and we all know that for aerogel, but maybe not for yours, because calcinated, it is not really good to have the complete view of the porosity of the material, because you know the story, the densification when the meniscus is appearing and so on. So probably trying to have the apparent density of your material. I know that it is difficult because it is a divided material. So, okay, but there are for sure some techniques which permit to characterize, to evaluate, to guesstimate the density of granules. And this permit, for instance, to have a view of the specific porous volume, and you can compare with your BCH volume, and maybe you can see that there is a porous volume which is lacking, and it can maybe be microporosity, and can answer to one of the questions of Corinne regarding, okay, your particles are constant and your specific area is increasing. So the microporosity could maybe contribute to answer this this part.
Yes.
Okay, so
Yes.
and it can come from a simple estimation or calculation of the density. This is the point. Okay, but it is too difficult. So it is only comment. This is the easy part of the discussion. And what I want to add also is that with the density in hands, maybe you can be able to have an idea of the mechanics of your materials, because at the end of your manuscript you have a very nice, very important and interesting observation you have shared with us, is that there is a deposit of copper on the window inside the reactor. We don't know why, but maybe there is a fragility in the mechanics of the samples, and that the sample is destroyed, or it is evolving during this experiment, and is okay, and there is a release of the copper.
Yes.
Okay, so having this density in hand, thanks to power law, Young modulus of rupture, and so on, you can maybe, not you, but the coming PhD student for sure can have some idea about this. Okay, this one can be fragile. This one can live with some stress, because there is a point I want to share with you. At the end, the photo reduction test, you have this aerogel in hands. You put it in water. So there is an intrusion of water inside your aerogel. Okay. The water, the liquid vapor tension of water is very high, so the stress could be very high, particularly because you are working with mesoporosity. So what do you think about this stage? Is there any change, probably, not probably, is there any change of the morphology of the samples during this phase or not?
Actually, it's not sure. It could be changed because the solvent change. It's not alcohol. It's changed to water.
Right.
So yeah, and we don't know exactly after it's absorbed the water what kind of morphology it is. So yeah, it could be changed. So actually, we don't know exactly what happened during the reaction.
Okay.
Yes.
Okay. So finally, mechanics of this product could have interest regarding the final application. So, okay, another thesis question. Good. Okay. Just a question regarding, and it has been underlined by everybody before me. This is a very complex system by itself, and particularly because you add complexity using co-doping, metal, and so on. So it is very, very dense. When we are looking at the slide, the 36, I guess everybody has pointed out this slide. This is 36 one. Alors, for a lazy person like me, if I am focusing on the two last columns, okay, there is a difference for sure. One is co-doped and one is only nitrogen doped. The difference is significant, huh? But it is a low. So can we live with only nitrogen doping?
Yeah, maybe nitrogen.
And copper deposit, for sure.
Yeah, could be because nitrogen. So for my case, in here, nitrogen is more compared to niobium is more benefit for methanol production, and I think it's maybe because nitrogen, the electron transfer for nitrogen is more easier. So yeah, so for here, that's why in the perspective, I was prefer to try to new way to for nitrogen doping.
For sure. No, but you improve, and particularly it is significant. But more or less a final question. But not only you have a lot of chemical product, co-doping, metal deposit, and so on, and you wanted during your PhD thesis to try to develop two elaboration phase to deposit, maybe it is not the good term, but to integrate inside your matrix the copper. The in situ, so to say in situ, or maybe we can say one pot, I don't know what is the term, but okay, the generation during the sol gel synthesis has shown very good results. So what is the reason to try to develop another one, an alternative route you called impregnation?
Yes.
What is the reason?
Yeah, this is because after have this result, I can say on the surface with more copper 1, even with more copper 2, getting the better performance. That means copper is improved. Copper in the surface is improved catalysis in moving, but in our case, for in situ case, the mode of copper is in the bulk, is not on the surface.
Okay.
So we try to use impregnation method to put more copper directly on the surface.
Very nice. Sorry, I didn't catch this point. There is some hidden or not accessible copper, and you want to increase this accessibility, and finally you try to change completely the synthesis work.
Yes.
Okay, very good, very good. So I liked very much the evolution regarding this impregnation process. At the beginning, you impregnate. There is still this problem of intrusion of water inside the porosity, but okay, you impregnate and then you dry in the oven and you make some xerogels. And finally, the specific area is something like 1 or 2 square meters per gram. So it is okay, peanuts, nothing. Then you said, okay, this is not very good way to work with. I'm going to have this supercritical drying. And this supercritical drying finally didn't work very well because of the elution of the particle during the solvent exchange, the water, which is not miscible with CO2. And then at this stage, something which is not so directly made by all the people working on aerogel is that finally you go a step further, a step back, not working with aerogel, but with wet gels, wet gels in the water. So this is a very, very smashing. I do hope that we can continue working on this because there is no washing. There is no problem of drying directly with the wet gel.
Yes.
So I guess that we can do something with this. Oh, what is the last question I can? But maybe a very simple question and maybe stupid too, but okay. Regarding you are working with granules of aerogel for your photo reduction test. Do you control the size of the granules? Or, so to say, is this size can have an impact on the efficiency of the photo reduction? I mean, regarding some diffusion aspects, for instance, millimetric, micrometric, submicrometric, tenths of micrometer.
It could be. It could be a factor. And in my case, I didn't change. I just using the same one. Just try to control the same parameter, and I just compare different catalysis. So, but in the different, this is also a factor. So it's also should be one of the factor to evaluate it to further.
Okay. Oh, I do want to share other things, but maybe we have time later. Okay, so I will stop there. Thank you very much for all of this.
Thank you.
Thank you so much. So now the last, I will give the floor to the supervisor.
Okay.
Okay, thank you very much, Miaomiao, for this very nice presentation. We'll first thank the jury also, and especially today, the very nice discussions we had. It was very long, but very, very interesting. A lot of different ideas arose during this discussion. So we will try to push the subject, taking into account all these very nice proposals. And so thank you very much for this time. Thank you very much to you, finally, because it was 3 years of very intensive work, but very, very appreciated from my side. We had a lot of discussions and a lot of very good interaction. The subject was not that easy. Okay, it was said we had some knowledge on the sol gel chemistry and aerogel synthesis, anti-IO2, niobium doped. You said it, but all the rest was new. We never worked on CO2 reduction, so it was brand new for us. You had to build a new test bench to bring your new ideas for this subject, so it was very fruitful. I found a lot of samples, a lot of work, a lot of characterization. Of course, we could have done more. It's always the case, but it's only 3 years. We have to stop at one day.
Yes.
I wish we could continue, but okay, you have to stop and you have to do something else. So I was very happy for this collaboration. We have plenty of ideas to continue the work. You mentioned some arose from the discussion. So I really wish that, okay, we will be able to find some funds to continue the research. And I hope we could keep in touch for the future. And I wish you the best for the future.
Oh, thank you.
So thank you for this nice discussion. So now we will go probably in small rooms. So I asked to Christophe and Valérie to connect to the other link now for the deliberation. So the suspense, it's important for you, intense. So you have few minutes to be quiet and to drink a lot also maybe to relax a bit and to prepare you for the deliberation.
Donc on se retrouve
So waiting you. Waiting you. We come back here after? Yeah. Okay. You're very nice. So the pressure decrease now. Ouais, c'est ça. Non, mais parce que c'est appréciable. Moi, je vois de ça.
Quand il y a le repas, là, ils sont en train de cavaler, ça dit non.
Maybe you can. Ah, no, this is one. Where is your presentation? Yes, it's this one? Maybe? No. There are many different, actually. It's very important for the picture. The photo. Yes. Do you have your phone? Ok, ça fait une photo. J'imagine que ça fait.
Allez, monte un peu. On n'a pas annoncé, on annonce. On va annoncer après. Ouais. Allez, ben, je crois que travaille dans les labos, ils peuvent pas gérer. Don't be afraid, guys. It's fun, It's a fun, yes.
Okay, your place is here.
Before and after. sur l'estrade. Allez. Allez. Non, mais vous allez nous faire le voir avant. Ouais. Ah ouais, directeur de thèse.
Ah ouais. Allez, allez, moi je prends la photo. Et le directeur, allez. Non, allez-y, allez-y. Moi, j'ai déjà fait la photo. C'est nice, I agree.
For free.